Okay, we are continuing on here with thermodynamics. Exciting. We we're talking about some stuff here that involves thermodynamics. I'm getting into my head here. I think it was Gibbs free energy we did a little bit of. And Gibbs free energy is delta G. And delta G will, I yelled out the other day that looks more like a G than a 6. There we go. Delta G will tell us whether or not a reaction is spontaneous. If we do have a -1, then it should be spontaneous or sort of head towards the product side. If it's a positive value, then it is non-spontaneous. And we saw a couple different ways, I think, to calculate delta G. Much like all sort of thermodynamic type properties, you basically can kind of do products minus reactants, where you can look up obviously the values there in the table. We also had one that involved delta H and delta S. And remember, obviously the temperature here does need to be in Kelvin, and the units you got to watch out for as well. Again, H is usually kilojoules, S is usually joules. And I think we also talked about there as well that sort of using this equation in sort of a phase change situation. When we are at a phase change, we are at a equilibrium type of process. And basically what that would mean is our delta G would equal 0, which gives us delta H minus T delta S. Kind of rearranging and solving for delta S here would give us delta H divided by T. And we could use this, for example, something like I think what we finished up on was the entropy of vaporization, which is the entropy change that occurs obviously as we do the transition from liquid to gas or backwards. Where the delta H here would, in this particular case, obviously be the delta H of vaporization for whatever substance you're dealing with, along with the temperature here that obviously doesn't even in Kelvin, but it would be, in this case, the normal boiling point for that particular substance as well. So if we were doing water, obviously that'd be 100 degrees Celsius or 373 Kelvin and about 40.6-ish kilojoules per mole. We also talked about that. Remember that when you sort of do this rearrangement using that equation in a phase change situation, there is no negative there. And this looks just like what we saw earlier on in this chapter where we calculated delta S of the surroundings, which is negative of the delta H of the reaction over the temperature. So remember that if you are doing the delta S of the surroundings, there was that opposite relationship in terms of the energy being released to the surroundings and the sign that we would expect. So sometimes people always want to kind of throw the extra negative into this one when they sort of do these type of problems. But remember, really, the only time you should throw the negative in there is if you're doing the surroundings part. Any questions on any of that stuff there? Okay, so it's been too long, so I feel like we should go back to our favorite letter of this class, which is K, right? So we can obviously relate Gibbs free energy, which, by the way, again, is, as the name implies, some type of energy that's basically free and available to do some type of work usually, and our equilibrium constant. And here to add to our growing list of ways to calculate G's, or some different ways to calculate G's, are a couple of other important little equations here. And let's take a look at each of these here and sort of talk about them. So this particular equation here that I just boxed has delta G is equal to delta G naught plus RT natural log of Q. And if you remember, we sort of talked about the little naught thing. When you sort of see that, that usually implies standard type conditions. And usually what standard type conditions means, again, is kind of what you see in table values. And that usually means that usually the temperature is 25 degrees Celsius. If you're dealing with any pressures, everybody should be a pressure of 1 atmosphere. And if you're dealing with any type of concentration, everybody should be 1 molar. So that's typically what's assumed in pretty much all like table type values, especially for thermodynamics. So when we see kind of the regular delta G there without the little guy on the top, you could kind of think about it, and again, maybe not 100% correct, but a good way to think about it is like a non-standard condition here. So basically one of those three things on the right there is not exactly what it says there. So maybe the temperature is not 25 degrees. Maybe you got some different pressures going on and stuff like that. Or maybe you got some different concentrations than 1 molar. So that's sort of the delta G under sort of what I like to think about it as sort of non-standard conditions. This delta G naught would be either given to you, or if you needed to calculate it, it would be the one most likely you would go to the table and look up the values and do your delta G of your products minus the delta G of your reactants. The R here is our gas constant. It is the 8.314 version there that has the energy sort of value in it. Temperatures are Kelvin. And Q is the same thing that we've talked about many times up to this point. It is the reaction quotient. And remember that Q is really calculated the exact same way as K. So it is the products over the reactants, and just like everything else that we do, obviously you take the coefficients as the exponents and all that good stuff as well. Or obviously as well, if you're dealing with pressures, it could be the pressures of the products really, you know, over the pressures of the reactants as well. So that's a sort of delta G equation that you would use. Again, like I said, if there's something that is, you know, just not under sort of normal sort of conditions, that probably would be the one that you would want to use there. When we do get to equilibrium, at equilibrium, delta G will equal 0. And we're no longer talking about Q, we would be talking about the equilibrium constant. So the top equation basically will reduce down here to the bottom equation at equilibrium. And it gets us delta G naught is equal to minus RT natural log of K. And these are all our same sort of characters here, or delta G naught, just like above, products minus reactants if it's not given to you or if you're not solving for it. R would be, again, our gas constant, the 8.314, temperature still in Kelvin, and obviously here the natural log of K. Also missed on both of these, are sometimes sort of mixed up on both of these guys, are the signs. This is negative, and it's negative because basically we are rearranging this equation up here and solving for delta G naught, so it actually is negative. And for some reason, people always want to like subtract here. So people always want to subtract that guy up on top. So it is a plus that you have going on there. So if we sort of keep track of what we talked about with delta G here, there are sort of 4 sort of different ways, if you will, or equations to use for delta G. As I mentioned before, sometimes the best way to sort of think about it is sort of based on the information given to you, perhaps pick the appropriate one. So again, if you're really not given anything, that's straight, go to the table, look up the values, do the products minus reactants. If you are given the H and the S values, then you would want to go into the H minus T delta S. If it has to do anything with equilibrium, that should probably bring you to the bottom equation here. And then obviously if it's something that, you know, they give you maybe some pressures, some concentrations that aren't standard, you're probably going to be using the top equation there as well. So again, that's sort of the simplest way to sort of choose which one would be the best equation to use. Any questions on that there? All right. So just like sort of the other equation, we can look at this equation and make some determinations. The good news about this one is it does have K in it. So again, if we understand what K means, it should also help us understand what we should expect for delta G. So if we did have a large value of K, this guy was large, what that normally means, right? If we have a large value K, we should expect reactants or products. We should expect more products, right? And the only way to get the products is to head towards the product side, going from reactants to products, which means typically our delta G here would be negative in this case to do that, as the reaction is written to head towards the product side. And vice versa, obviously, if we had a smaller value of K, that again would mean that we would expect mainly reactants at equilibrium. That means the only way to sort of get reactants is to stay over there on the left-hand side of the equation where the reactants is favor, and that means probably the delta G is going to be positive. It's not going to make the reaction go to the right. It's just going to kind of stay there on the left-hand side. If we have a K value that's 1, reactants and products are kind of there in the same ratio. Obviously, us, the only way you could kind of get 1, right, is to have basically the same number on top and bottom when you divide. And again, delta G will also equal 0. So you may be in a sort of equilibrium process, not going one way or the other. All right, so let's take a look at some examples here. Why don't you try this one here? Calculate the equilibrium constant for the following reaction. Here's some table values that you can find for delta G. I will add the O2 in there for you for free. It is 0. By the way, these are kilojoules here, yes. Okay, let's take a look at this one just to make sure. So we are looking obviously for an equilibrium constant. So clearly that should point us to the only one that we saw that does have obviously the equilibrium constant involved. R obviously is a constant, which is our 8.314 joules per Kelvin per mole. And temperature here does need to be converted there into Kelvin. So that would give us a 298. And in this case, we're not given the delta G. So we would again go to a table to calculate the delta G. And if we did that again, it's going to be our products, which in this case is O2. So that's a big whopping 3 times 0, I think. Minus our reactants, which is 2 times our 163.4 kilojoules. And that will get us 2 times 163.4, looks like a negative 326.8 kilojoules. Any questions so far? At this point, we can put in our numbers. That would give us negative 326.8. I'm going to times it by 1,000 to convert it to joules because my R is in joules. So everything cancels out sort of correctly here. Is going to equal our minus 8.314 joules per Kelvin per mole and our 298 natural log of K. I'm going to bring everybody to the other side there. And if I do that, 8.314 and divide by a 298er, we'll call it a 131.9 equals the natural log of K. Also, don't forget there is a negative here, right? That will turn our negative here into a positive. So we want to make sure of that. To get rid of the natural log, right, we need to take the E, right, of both sides there. So we'll do that little move and that little move. That is going to give us just K on the right-hand side. If I hit the right buttons here, we'll hope for the best. And that will give me a 1.9 times 10 to the 57, looks like, as our equilibrium constant. Any questions on that? Now, we should see that our numbers sort of agree with each other, and they do, right? We have a delta G that is negative, which means it should be heading to the product side, which means we should have a lot of products when we're all said and done there. And obviously, we have a K value that is a large value, which would also imply, obviously, we have a lot of products at that point. So again, those two numbers should agree with each other. Obviously, if we had a positive guy, we should have a smaller value for K when we calculate it. Any questions on that particular one there? Again, like I said, a couple places where people sort of mess up is unit-wise. They leave 1 in kilojoules and 1 in joules, and also the negatives is, again, a very common sort of error. Any questions on that one? All right, let's try another one here then. Calculate the delta G naught for the following at 25 degrees if the KSP is 1.7 times 10 to the minus 6. Okay, so once again here we have something to do with the equilibrium constant. Remember, it doesn't really matter what type of equilibrium constant it is. They're all basically the same thing. So once again, we would use the same equation. In this case, we pretty much have everything on this side, so we just need to plug it in, I think. So our delta G naught will equal or minus 8.314. Our temperature, once again, converted to Kelvin gives us a 298. A little natural log of our KSP, 1 times 10 to the minus 7 times 10 to the minus 6. So we will get natural log 1.7 to the minus 6 times a 298 times an 8.314. No more timesing, perhaps. And that will give us 32914.25243. I did not feel like rounding there. That will give us joules, maybe divided by 1,000, get a little nicer looking number there, maybe like a 32.9 kilojoules. Kind of clean it up a little bit there. Any question on that calculation? Do these two numbers agree? The K value and our delta G. They do agree with each other, right? We have a very small K value like we would expect with the KSP, which means we're mainly singing out on the reactant side, which means with a positive delta G, we would expect mainly reactants and it not being really spontaneous. So it's kind of just staying there on the reactant side. So again, each of those things do agree with one another. Any questions on that particular one there? All right, one last one here, I think, to finish up the chapter. There we go. The delta G naught for the following reaction is 2.6 at 25. In one experiment, we got some pressures, 4.26, 0.024 for our I2, and 0.23 for our HI. Calculate the delta G for this reaction and predict which way it will head. Look, so in this case, we were given a delta G naught. We are looking for another delta G. So really the only equation that kind of had double delta G action going on there was this one here. And again, that is a plus there, RT natural log of Q in this case. We also know that this is sort of non-standard conditions because when we look at the pressures here, they are not all 1 atmosphere. So that would put us into a non-standard type of condition. So we do need to calculate Q. Q in this case would be our products over reactants, which since we're dealing with pressures, would be the partial pressure squared of HI divided by the partial pressure of H2 times the partial pressure of I2. Putting in our numbers there is, if I grab the right one, let's go with 0.23 divided by 4.26 and 0.024. That is going to give us a Q of a number. Squareage, a little dividage, one more dividage there. It's an equals. I'm going to go with a 0.517 as our Q value. Clearly as well, we do need to convert our temperature into Kelvin. R, once again, is the same constant. And they actually did give us our delta G naught. So once again, if they didn't, you would go to the table, obviously, and calculate it that way. So we'll just roll it right here. Delta G equals our delta G naught, which was given to us of 2.6. So once again, I am going to multiply by 1,000 to put it into joules like my R value once again. So everybody's in the same units. I'm going to add it to my 8.314, which once again is the joules, our 298, and our natural log of 0.517. There we go. All right, so if we kind of clean up the right-hand side there of the plus sign, we will get times 298 times 8.314 gets us a delta G that is equal to 2,600 joules plus minus 0.1632. It looks like a point, I think, 0.52 joules. At this point, we can add these together. It gives us 2600 plus a negative 1632.52. Now we'll call it roughly 967 joules, I believe. I didn't screw that up. Any questions on that calculation there? All right, so this means is reactants or products favored in this case? Delta G is positive, which means we would expect reactants at this point. Kind of going this way, kind of a non-spontaneous type of deal happening. We can actually see that because when we look at the pressure, the major pressure is which one? This guy, which is a reactant. Yeah, so that all kind of fits together nicely. Any questions on any of that there? Questions on thermodynamics, delta G, any of those things? All right, that wraps up this chapter. Good deal. All right, talk about sort of redox reactions and balancing redox reactions. So, you know, depending on maybe who you had for Chem 50, you may have different degrees of knowledge on this topic. So we're just going to kind of go over some of the basics of redox reactions and stuff like that and how to balance them in acidic and basic conditions. So hopefully everybody will be sort of on the same page. First off, redox, right, means oxidation and reduction reactions. And there really is several definitions for each of these. Oxidation typically means the loss of electrons. It can also mean the gaining of oxygen or the loss of hydrogen as you go from reactants to products. While reduction typically means the gaining of electrons. Also can mean the loss of oxygen as you go from reactants to products, or the gaining of H2 or hydrogen as you go from reactants to products. I would say for the most part in our chemistry here, in general chemistry, it is pretty much all about kind of the electrons is typically what we focus in on. If you go on to take organic chemistry, I'm sorry, but if you go on to take organic chemistry, you will look at oxidation and reduction in terms of oxygen and hydrogen. Sometimes that's more what you look at than electrons. But here in general chemistry, usually is sort of the transfer of electrons. That's why some people remember this by Leo the Lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Yes. Oxidizing is losing, reducing is gaining. Not reducing, yeah, reducing is gaining. There it is. Sounds right. You can use them together. You can put Leo the Lion on the oil rig and he goes grr, then you don't have to choose and all that good stuff. All right, so let's take a look at each of these things here and sort of talk about some of the stuff that's happening. Obviously, in an electrochemical process, which are oxidation reduction reactions, the energy released by a spontaneous reaction is converted to some type of electricity. Essentially, it's all about the electrons being transferred. Electrons go out, do some type of work, and then kind of come back, right? One of the driving forces for why chemical reactions occur is basically the transfer of electrons, right? There's really three reasons why sort of chemical reactions actually occur. The transfer of electrons is one important one. The formation of a solid or a precipitate, or the formation of water, really the three reasons why chemical reactions occur. Redox reactions is sort of a big umbrella of reactions, right, that can be classified a more specific way that you probably learned. Things like synthesis reactions and decomposition reactions, single replacement reactions, combustion reactions. These are all also redox reactions that are happening, even though we sometimes classify them more specifically based on what's going on. While when you have something like a precipitation reaction or a acid-base reaction where you make a solid or a form water. That's under the big category of double displacement reactions, is where those guys basically fall into place. When we look at one like this, which is technically a synthesis reaction, it is also really a redox reaction that is going on. When we have things by themselves on the left-hand side there, their oxidation state, which we'll talk about in a second as well, again, not necessarily the charge, but their oxidation state. Do they have any type of charge or any oxidation state on the left-hand side here? They are by themselves. They have absolutely zero in terms of oxidation numbers, right? It is only when like a metal and a non-metal on the right-hand side get together that they actually do form a charge and make an ionic compound. And that is when magnesium gets the +2, right? And the oxygen there gets the -2 that occurs. So this is really a reduction and oxidation reaction that's happening, and we can figure out what's happening. And if you're not really sure maybe who's being oxidized or who's being reduced, there's really a very simple way you could kind of figure it out. And you could just do like a very simple number line where 0 is usually there in the middle. To the right of that 0 usually is positive numbers. To the left there is negative numbers. When we lose electrons, do we become more negative or more positive? Yeah, you do, right? Because when you lose electrons, you got more protons, right? So you become more positive. So if you find somebody on the left-hand side of the equation to the right-hand side of the equation, their oxidation state is becoming more positive or sort of moving in that direction. That is the guy that is going through oxidation. Vice versa as well. Obviously, if you gain electrons, you now have more electrons than protons, and you typically become more negative, which means if you find somebody from the left-hand side to the right-hand side that's becoming more negative or sort of moving in that direction, it is going through reduction here. So if you weren't sure here, you could very simply just use that little number line to help you figure it out by saying my magnesium is starting at 0. And on the other side of the equation, it becomes +2, which means it's moving in this direction. And that will tell me that the magnesium here is going through oxidation. While the oxygen started at 0 and it ends at -2, which means it's going in that direction and it's becoming more negative, which means the oxygen here is going through reduction. Any questions on that? By the way, when you have a metal and a non-metal that come together, which one always loses electrons? The metal always loses the electrons, the non-metal always gains the electrons. So that's a quicker way to know that, is like the metal should be the one losing it. But sometimes you have metals and metals sort of in the same reaction that you're looking at. So you have to sort of figure it out. We could take this overall reaction and write what is referred to as 2 half reactions, which is basically one half is the oxidation reaction that's happening, and the other half is the reduction reaction that's happening. So because magnesium is going through oxidation, we would start with the magnesium. It will form its +2 charge and will give off 4 electrons overall. And we know that this is the oxidation half reaction because the electrons are found on the product side. So the electrons should be on the product side. In this balanced equation, we have 4 electrons. That's because there's 2 magnesiums, right? Each magnesium loses 2 electrons. 2 times 2 is 4 electrons are being transferred. Again, 2 electrons from each of the magnesiums. In this case, the oxygen will actually gain those electrons, those 4 electrons there, and form our oxygen with a -2 charge. And we know that this is the reduction half reaction because the electrons are on the reactant side. This is considered half reactions because, frankly speaking, you super zoom, then you zoom out. If you take both of these half reactions and add them back together, anything that's on opposite sides of the arrow will cancel. And by the way, when you do this, it always should be the electrons that completely cancel out. You should always have the same number of electrons in each half reaction before you add them back together. And that means sometimes you may have to multiply a half reaction by a common number to get everybody to the same number of electrons. Sometimes you need to multiply both of them by a common number to get to the same number of electrons. The reason for that is it is a perfect equal process, if you will. However many electrons that the magnesium loses should be how many electrons the oxygen gains. So it is a complete transfer of electrons, and we have the same amount of electrons on both sides. And if we do that, everybody on the left-hand side of the arrow stays on the left. Everybody on the right-hand side of the arrow will stay on the right-hand side of the arrow. We have two ions, +2 and -2. They will come together to make 2 units of MgO in this case. Any questions on that there? So when you write your half reactions, oxidation should always have electrons on the product side. Reduction should always have them on the reactant side like they're being gained. And before you add these two half reactions together, you need to make sure you always have the same number of electrons in each one. And you should always try to balance them out as well. Make sure everything is balanced. We look at another example here. We have our calcium and our oxygen coming together in another synthesis reaction, which again is a redox reaction. 0 oxidation number here, 0 oxidation number here. When the calcium and oxygen come together, that once again is where our calcium becomes +2, our oxygen becomes -2. And once again, if you're not sure, you could just follow what's happening. Calcium once again starts at 0 and ends at +2, which means it's going in the oxidation direction. Oxygen starts at 0 and ends at -2, which means it's becoming more negative and is in the reduction situation here. So once again, this is going through oxidation. The oxygen is going through reduction in this case. Once again, we see our two half reactions because we have 2 calciums. Each one's going to lose 2 electrons. That is how we get the 4 electrons. And obviously the oxygen here will gain the 4 electrons. Those guys will cancel each other out and leaves us our overall reaction that is happening right there. Any questions on that there? So let's talk a little bit about reducing agents and oxidizing agents. So an oxidizing agent is always the substance that gets reduced, while the reducing agent is always the guy that gets oxidized. So the agents are sort of opposite of their names, and the reason they're opposite of their names is that is what they cause in the other substance. So obviously, if somebody gets reduced, it needs to gain electrons, right? And the only way for it to gain electrons is to cause somebody else to lose electrons. So it is causing that guy to be oxidized, which is why it's known as the oxidizing agent. Same thing here. Somebody's going to get oxidized and lose electrons. That means somebody needs to be there to pick up the electrons. So it's going to cause somebody else to pick up those electrons and be reduced. So in our couple of examples there, the magnesium plus the oxygen and our calcium there plus the oxygen without the, do that. This guy here was again the one that is being oxidized. So that means it is the reducing agent, while the oxygen there, which is being reduced, would be our oxidizing agent in this case. And same thing up here, our magnesium would be oxidized and be the reducing agent. And once again here in this example, our oxygen would be reduced and be the oxidizing agent. What is being reduced? What is being oxidized? What is your reducing agent and oxidizing agent? They all should be reactants. Yeah. So, and when you're asked that question to identify those things, you should be specific. Yeah. So you shouldn't just write like magnesium, you know, whatever. So if it is magnesium, you should write magnesium. But if you wrote like this guy, that is incorrect. Yes. So it is this guy that is actually going through the process. If you just write O, that would be wrong. It should be like this guy, yes? So you want to make sure that you're specific when you're identifying those and not just kind of lay up like an element and let me choose. But all four of those things, if you're asked what's being oxidized, what's being reduced, or what's the oxidation agent and reducing agent, they really should come from your reactant side of the equation. Any questions on that there? As I mentioned before, we don't do too much of this in here. And again, more in sort of organic chemistry, you kind of use those other definitions of oxidation and reduction, gaining and losing oxygen. So for example, here, if we look at our tin, it is going from oxygen on the left to no oxygen on the right. So that has lost oxygen, which is a definition of reduction. By the way, the other nice thing is if you can identify one, the other substance is the opposite thing happening, right? So you just need to be able to identify one in a lot of cases. The carbon in this case is going from no oxygen to oxygen. So that is a definition of oxidation. That is why the carbon here would be our reducing agent because it's going through oxidation, while our tin 4 oxide would be our oxidizing agent in this particular case. The nice thing about this one is actually there is a metal involved, which means you could actually figure it out based on the metal. The tin on the left-hand side does have a +4 situation. Tin over here has a 0 situation going on. And once again, it is starting at +4, which would be here, ending at 0, which means it is going to the left and becoming more negative. And it should be going through reduction, which is what we deduced over there. So if you have something with a metal, you could still kind of look at obviously the oxidation numbers. Any questions on that there? So oxidation numbers is a really important thing, obviously, in redox reactions. Sometimes people get really confused about oxidation numbers, and again, sometimes called oxidation states. Because they look at it and go, wasn't I beat into my head that chlorine is always -1? So it's always -1. But something like chlorine, for example, could be -1, and in certain situations could be like +3, you know, +4, whatever it may be. So it can have different oxidation numbers or states. So the oxidation number and state is not necessarily always what you sort of learned when you talked about sort of ionic compounds. If you are dealing with an ionic compound like we just were a second ago with the tin, it is going to be the same thing. Basically, the oxidation state and the charge will be the same. But where oxidation numbers really are different than we sort of envision them or maybe have learned them before is when we're dealing with covalent bonding and covalent molecules sharing electrons. So when everybody shares electrons, different elements in a compound, when they're sharing electrons will take on sort of like a different sort of charge, if you will, based on how many electrons and bonds and stuff that are happening. And that's sort of what the oxidation number sort of represents. So let's talk about some of the rules that we follow when we apply oxidation numbers or states. First off, the first one is pretty simple. If you have any element that's pretty much by itself, it's uncombined with anybody else, it will always have an oxidation number of 0. Any monoatomic ion that's by itself, the oxidation number will be the same as the charge. So again, if you have something like iron 3 chloride, the oxidation number would be +3 for the iron. The oxidation number of oxygen is usually -2, and that's usually a really good place to start with if you do have oxygen that you have in the compound, to start with the oxygen. The one exception is if it is like peroxide, like in hydrogen peroxide, it would be -1, and that's because peroxide is a polyatomic ion there. But probably in most cases, it will be the -2. How do you know it is peroxide? Usually there'll also be an extra 2 in the first guy there along with it. So that's usually how you can kind of tell. Couple of other important rules. The oxidation number of hydrogen is +1, except when it is bonded to a metal or comes second. And that is when it's like hydride, which it is -1. So obviously if you had something like lithium hydride, lithium is +1 and the hydrogen here would be -1. Other than that, if it's not attached to a metal, it's going to be +1. Everybody in group 1 and group 2 will have the respective sort of charges, +1 and +2. Fluorine's always -1. When we add up all the oxidation numbers, they do need to equal the charge on the ion if it is an ion. So if it has an overall +1 charge, when you add up everybody's oxidation numbers, it needs to equal +1. If it has a negative charge, it needs to equal whatever that negative charge is. And obviously, if it has no overall charge, when you add up all the oxidation numbers, it does need to equal 0. So why don't you give this one a go here, see what you come up with. What is the oxidation numbers for everybody in bicarbonate? Okay, let's take a look. So like I said, in a situation like this, especially in a situation like this where you got like 3 elements, usually you kind of want to start with the oxygen if it's there. Kind of want to go on the outside and save the guy in the middle for the end. So if we started with the oxygen, it would be -2. There are 3 of them, which gives you kind of like an overall sort of charge there of -6. Going to the other extreme there on the other end is hydrogen, which is +1. So that would give you like a +1. So at this point, I have +1 and -6, which is -5. I do need to end up with a -1 when it's all said and done, which means the carbon in this case is going to be +4. +1 + 4 is +5, -6 gives us a -1 left over. So just so we're clear, if you were to give the oxidation numbers for hydrogen, it should be +1. If you're given it for carbon, it should be +4. And if you're given it for oxygen, it should be -2, not -6. So not the grand total. So when you're asked to give the oxidation number or state, it is just for one by itself. And it should have the charges. So if it's positive, you should put +1, +2, whatever it may be. And if it's negative, you should put the negatives in there as well. Any questions on any of those there? All right. So once again, that would be the proper way to report all of these guys here. All right, take a look at a few more examples here to finish it up for today. Give the oxidation numbers of everybody there for each of these guys. Let's take a look. So starting the first one here, that is oxygen, which would be -2. And this is lithium, which is a group 1, which will have the same as is normal. So again, for Li, it would be +1. And for the oxygen here, it would be -2. Any questions on that one? Fluorine is a good place to start. It is always going to be -1, and there obviously is 3 of them, which gives us a -3 overall. There's no charge, which means to balance it out, the phosphorus here will actually be +3 in this case. Again, phosphorus you may think of as -3, but in this configuration, sharing of electrons, it's actually going to take on a +3 sort of oxidation state. Any question on that one there? Going down to our nitric acid, this is -2 there for our oxygen, gives us -6 overall. Again, leaving the guy in the middle for the end. Going to the other side is +1. In this particular case, the overall charge here is 0. So to balance that out, it would be a +5, I believe, to do that. And that should get us to 0. So hydrogen here should be +1, nitrogen should be +5, and oxygen should be -2. Any questions on that one? Lastly here, a little dichromate action. Oxygen being -2 gives us like a -14. Overall, we do want to end up as a -2 because of that. We, in this case, actually have 2 chromiums, which means in this case, each chromium is going to be +6. Sounds like a winner. That's going to be +6, gives us a +12, -14, -2. So once again, though, the chromium here will be +6. The oxygen will be -2, and that is the correct way to report the oxidation numbers are states. Any questions on assigning oxidation numbers? All right, we were laid up there. I think